Right now, a mysterious object from deep space, known as 3I/Atlas, is racing through our solar system. It's not just moving fast, it's getting brighter every few weeks, and surrounding itself with a glowing green cloud that now stretches over 500,000 kilometers wide. It's currently on a path toward Mars, and what scientists expected to be a small flicker in the sky has turned into something much more dramatic. 3I/Atlas is now shining nearly 6 times brighter than experts had predicted, leaving astronomers puzzled and prompting a wave of questions. Could the bright outburst be caused by intense activity in the comet's core? Is sunlight reacting with unfamiliar ices? Or could it be something no one has seen before? As the object nears its closest approach to Mars in the coming weeks, and with Earth's view soon to be blocked by the sun, scientists are racing against time to find answers. Before this fast-moving visitor disappears from sight, researchers are trying to understand what's powering its unexpected glow and what secrets may be hiding within that bright, expanding cloud. At the moment, 3I/Atlas is about 2 astronomical units from the sun. That's around 300 million kilometers, or twice the distance between Earth and our star. Its speed is staggering. It's currently traveling at nearly 60 kilometers per second and picking up even more speed as it moves. By the time it swings closest to the sun in late October, it's expected to hit speeds of 68 kilometers per second. For perspective, that's more than double the speed of any planet in our solar system. At that pace, it could travel from Earth to the moon in just over an hour. When it comes to visibility, 3I/Atlas has now reached a brightness level called magnitude 12. While that might not mean much at first, it tells us the comet is far too dim to be seen with the naked eye. Even experienced stargazers need a decently sized telescope and very dark skies to catch a glimpse. To give you an idea of scale, an object with magnitude 12 is about 250 times dimmer than what the human eye can normally see, around magnitude 6. Despite its dim appearance to the human eye, the comet's brightness has been increasing far more rapidly than any forecast had suggested. The gas and dust surrounding the comet, the coma, has grown at a shocking rate. Current estimates show it may now be as wide as Jupiter. This enormous cloud isn't just for show. It's the main reason telescopes are detecting so much light from the object. As the coma expands, it reflects and scatters more sunlight, making the comet appear brighter, even if its actual solid core stays hidden from view. Observatories around the world are keeping a close watch. The Atlas team, who first discovered the comet in early July, is logging every new change in its position and brightness. These updates help improve trajectory models and alert the Minor Planet Center if anything unexpected happens. As 3I/Atlas heads toward both its closest pass by Mars and its nearest point to the sun, astronomers are paying close attention to its distance, speed, and brightness, 3 key numbers that will shape what comes next. In early September, something surprising happened. 3I/Atlas brightened much faster than anyone had expected. Its light curve, the chart that used to track how an object brightens or dims over time, suddenly changed course. This wasn't a slow or minor shift. It was a sharp and unexpected spike. That jump set off a wave of discussion among scientists and amateur astronomers alike, all trying to figure out what's really happening with this strange interstellar visitor. The coma, the enormous growing cloud of gas and dust encircling its hidden nucleus, is the central component of the riddle. In telescopes, the entire object appears brighter as the coma expands because it reflects and scatters more sunlight. The window for Earth-based 3I/Atlas observations is rapidly closing by early October. The comet gets closer to the sun's brilliance every evening as it descends farther into the twilight. By October 21st, the angle between 3I/Atlas and the sun, which astronomers refer to as solar elongation, has decreased below 30 degrees. Even the biggest ground-based telescopes have trouble distinguishing the comet's dim light from the sky's overwhelming brightness at that threshold. The comet hardly breaks the horizon before disappearing into the haze, and for the majority of the world, the window for practical observation has already shrunk to a brief period of time shortly after sunset. The last acceptable photographs are being snatched by amateur networks. As onlookers scramble against the approaching twilight, online forums are awash with tales of missed opportunities and rare successes. In an attempt to get a few more frames before the conjunction blackout, some teams plan worldwide campaigns, transferring observing responsibility in a relay from one longitude to the next. Professional observatories have already begun to retreat, constrained by more stringent safety regulations for their delicate optics. Few are ready to take the chance of damaging equipment by pointing it too close to the sun. Lost photos are not the only reason for the haste. There will be a full data outage after 3I/Atlas passes behind the sun as seen from Earth. No spectra, no direct measurements, and no means of monitoring changes in structure or brightness. This means that every last observation made before October 21st is crucial for astronomers. The comet will slip out of reach just as it's about to enter its most active phase. Because the solar system's geometry is closing the door, assets located distant from Earth's line of sight will be the sole hope for continued monitoring, a challenge that today falls primarily on spacecraft orbiting Mars.
The only outpost with a front row seat to 3I/Atlas is Mars for a limited time. The emphasis switches to a fleet of orbiters circling the red planet when Earth-based observatories go dark in the sun's glare. Every mission offers a unique perspective. With its Omega spectrometer and high-resolution stereo camera, the European Space Agency's Mars Express is capable of taking pictures and identifying chemical fingerprints from millions of kilometers distant. Equipped with NOMAD and ACS spectrometers, the ExoMars Trace Gas Orbiter is intended to detect subtle indications of gases, water, carbon dioxide, and potentially unusual volatiles within the comet's coma. While its plasma instruments track the interaction between the solar wind and this interstellar visitor, NASA's AMAVEN, which was constructed to investigate Mars' upper atmosphere, may adjust its ultraviolet spectrograph to detect emissions from the comet's gas and dust. Although tracking a fast-moving comet is difficult for any spacecraft, Mars Reconnaissance Orbiter, which is well known for its crisp, high-rise camera, has the ability to discern the nucleus if circumstances permit. Mars is favored by the geometry. In order to allow these orbiters to try direct observations, 3I/Atlas sweeps within about 28 million kilometers of the Earth on October 3rd. However, it is still far enough away to circumvent dust's hazard guidelines that previously hindered comet flybys. Weeks have been spent by instrument teams negotiating valuable observation opportunities, revising ephemeris files, and running simulations. Each team wants a piece of the encounter, including plasma data to examine the comet's interaction with the solar wind, ultraviolet spectra to assess gas generation, and visible and infrared photos to map the coma. The goal is to map the chemical composition of material emitted as the comet warms up and to capture the nucleus as a discrete point from the vast coma. No mission has guaranteed continuous coverage. Plans for observations are influenced by data bandwidth, spacecraft pointing limitations, and the uncertain date of the comet's closest approach. Direct measurements of dust, gas, and plasma at a scale never tried for an interstellar object, however, could provide insights that are not achievable from Earth. The focus is currently on Mars, and the scientific teams are prepared to take advantage of this unique chance before 3I/Atlas moves on toward its rendezvous with the Sun. The dazzling green glow of 3I/Atlas is the first thing that people notice about it. Spectral experts swiftly focused on this color, searching for chemical fingerprints in the comet's light. UV-stimulated spectra from both professional and amateur teams support the conclusion that diatomic carbon, or C2, is the primary offender. Coma patients' carbon-rich molecules are stimulated when exposed to sunshine. These molecules release a bright green light as they relax, particularly in the swan bands at 510 nanometers. Even when viewed from a distance of 2 astronomical units, 3I/Atlas stands out for the intensity of its green tint, which is a common signature for active comets. On the specifics, there is disagreement. Particularly in the early September spectra, several researchers have identified potential contributions from ionized carbon monoxide, CO+, or the cyanogen radical, CN. Additionally, both of these can glow green or blue when exposed to solar ultraviolet light, and disagreements regarding calibration scripts in background subtraction handling have surfaced in peer-reviewed forums. However, the cleanest, broadest spectrum coverage records, which are the most robust, consistently demonstrate that the visible coma is dominated by C2 emission. This chemistry goes beyond a simple aesthetic impression. Solar radiation is hitting fresh ices and dust at a faster rate because of 3I/Atlas's high speed, which causes volatile molecules to be peeled off and mixed into the coma. Therefore, the green hue serves as a real-time measure of how rapidly the comet's surface is changing as it accelerates toward the sun, rather than only serving as a marker for carbon. More and more onlookers are beginning to notice that 3I/Atlas looks strange. A slight sunward bulge that extends back toward the sun, this so-called anti-tail is in contrast to what most people expect from a comet, which is typically a characteristic tail pointing outward as dust is blown away from the sun by radiation pressure. In 3I/Atlas, the physics and geometry are working together to change the course of events. Dust grains expelled from the nucleus can actually travel ahead of the comet's course when it accelerates through the inner solar system, as 3I/Atlas is currently doing. This is especially true if the grains are large or electrically charged. These particles have the ability to project a thin sunward spike from Earth's perspective, with an anti-tail that is only discernible when the viewing angle is precisely aligned. Plasma physicists explain that the comet's fast velocity and the coma's rapid expansion provide a complex environment where electromagnetic forces compete with gravity. Narrow streams can form from charged dust grains trapped between the comet's own outflow and the solar wind. These sunward features change over time. They depend on the interaction of charge, grain size, and the constantly shifting sun's direction. The unusual viewing geometry in late September, when Earth is almost in the plane of its dust sheet due to 3I/Atlas's orbit, intensifies the effect. A sunward anti-tail on 3I/Atlas has not been confirmed, although some professional teams and amateurs have identified potential clues. No peer-reviewed photos or exact measurements have been released. Though its occurrence on an interstellar object at these speeds is rare, the phenomenon itself is not new to comet science. As 3I/Atlas hurtles toward the sun, the anti-tail, which already adds a layer of interest to an already unpredictable visitor, hints at the intricate dust plasma physics at work. Though each comet that passes through our solar system has its own quirks, 3I/Atlas is unique even in its small company.
Astronomers' expectations were established by the first two interstellar visitors, Oumuamua and 2I/Borisov. Oumuamua was a dried, cigar-shaped item that was found in 2017. There was only a tumbling fragment that barely made it past the inner solar system, with no tail or noticeable coma. 2 years later, with all the characteristics of a classic comet, 2I/Borisov made its appearance. Like the ice wanderers that round the sun every few centuries, it had a chemical signature dominated by water and cyanide, a vivid blue-tinged coma, and a dust tail straight out of a textbook. However, 3I/Atlas defies easy classification into any group. Due to substantial diatomic carbon emission, which is uncommon at this intensity in most solar system comets, its coma is not only vast, but also strangely green. Neither the gradual rising of Borisov nor the muffled transit of Oumuamua can compare to the brightness increase, which is over 6 times higher than expected. Additionally, 3I/Atlas suggests a sunward anti-tail, which is more typical of the rarest solar system comets, but almost unheard of in objects from interstellar space, even if Borisov's tail streamed away from the sun as predicted. 3I/Atlas is in a class by itself, even among recent newcomers like C/2025 R2, Swan, and a 6 Lemon that showed their own bursts of energy. Astronomers are forced to reconsider the distinctions between comets formed in nearby planetary systems and those formed in distant ones due to its speed, chemistry, and unpredictable behavior. Assigning a label is not the only problem facing classification teams. The physical processes that may have formed tiny bodies throughout the galaxy are revealed by each anomaly in 3I/Atlas's playbook. The stakes are really high. Decades of preconceived notions about what it means to be a comet and what tales these visitors can provide about the worlds they left behind could be upended by each new measurement. After perihelion, 3I/Atlas will start to wane, probably much more quickly than it brightened. As the comet accelerates away from the sun, its coma shrinks and disperses into the darkness, causing a dramatic decline in apparent magnitude according to most models. The conditions only get stringent for anyone trying to obtain a peak. The bare minimum is a telescope with a mirror at least 20 centimeters in diameter. Even then, the smallest smear will be detected by the most sensitive digital cameras. The comet will recede quickly, outpacing visual observers, and following any residual activity will need meticulous background reduction and image stacking. Online dashboards and coordinated campaigns are now the practical aspects of comet viewing. Near real-time updates on the comet's position, brightness, and morphology are provided by citizen science networks, some of which are based on Discord servers and others that are run by reputable institutions. These websites gather unprocessed data from backyard telescopes all over the world, process it using open pipelines, and provide post-light curves that anybody may use. For many, it's the first time that amateurs are documenting the destiny of a truly interplanetary object in near real time. The fade is not the end of the stakes for science. Each new piece of information, light curve, spectrum, and contested detection, adds to the larger picture. How do interstellar comets behave as they travel through a solar system so dissimilar from their home? What can we learn about the fundamental elements that formed planets around the galaxy from their chemistry, dust, and waning light? As 3I/Atlas disappears back into the shadows, the questions now extend beyond the observing field, encouraging anybody with a telescope, a laptop, or even just a natural curiosity to join the quest for answers. The October 3rd Mars flyby is the final chance for close-range multi-instrument observations because Earth-based views will disappear after October 21st due to superior conjunction. There are gaps in our understanding about incoming data since Mars orbiters have not yet issued comprehensive mission schedules. 3I/Atlas has a combination of comet-like and unusual characteristics in contrast to Oumuamua and 2I/Borisov. Its composition, fading rate, and structural behavior, as well as what happens when it rounds the sun, will inform future studies of interstellar visitors. Until its next near encounter, the true nature of 3I/Atlas is still an open scientific topic based on hard-won facts.